Okay folks, this is the second walkthrough of today's work. So we're going to look at the quick checks halogenoalkanes B and halogenoalkanes C. The first three answers to 1A, 1B, 1C I've just put on the board already. So what is a nucleophile? It's an electron paired donor or a lone pair donor. Why can the carbon-hydrogen bond react with nucleophiles? We need to specify that the CX bond is polar. You might want to give a bit more information as to why it's polar. So the halogen is more electronegative than the carbon, so you get an asymmetric distribution of electron density within the covalent bond. And therefore, what is attracted to, or what do nucleophiles attack? It is the partially positively charged carbon. But rather than writing those words out, you can just put that symbol with the delta positive in your answer. And then why does the iodoalkane react faster than the chloroalkane? Remember, it's nothing to do with bond polarity because the carbon-chlorine bond is more polar than the carbon-iodine bond. So it's everything to do with bond enthalpy. So the carbon-iodine bond is weaker, has a lower bond enthalpy. It's easier to break, therefore it's more reactive. And then we've got to write some equations between bromoethane, which is this, and hot ethanolic potassium cyanide. And the words hot ethanolic will throw a lot of you because you might be thinking that this is elimination, but remember, elimination only happens with hot ethanolic hydroxide ions. It's potassium cyanide, so it's the standard nucleophilic substitution. And what do? We swap the Br for the Cn. So we end up with this and KBr as a byproduct. So the name of this thing is propane, don't forget the E, nitrile. Really useful organic mechanism this, because you go from a 2-carbon chain to a 3-carbon chain. So in organic chemistry or organic synthesis, you're trying to build a molecule by lengthening the carbon chain. This is the type of reaction you might want to start with. The second one is 2-iodobutane with hot concentrated ammonia solution. So 2-iodobutane with ammonia. With ammonia in nucleophilic substitution, don't forget you'll need 2 molar equivalents. One because the ammonia acts as a nucleophile and then it acts as a base. So the first step, you're going to be swapping that iodine for an ammonia and then a hydrogen 4, so you end up with an NH2 group. You could do the mechanism out if you want to first, so you could do the mechanism and then write the equation from that. I've seen students do that before and it's really served them well. But you'll end up with that thing there and NH4I. Okay, and we'll do the mechanism for that to show it in a moment. Don't worry about naming this thing. You could call it 2-aminobutane, but again, we worry about naming amines in year 13. And the final one is the 1-chloropropane with warm aqueous sodium hydroxide. So warm aqueous should suggest to you nucleophilic substitution. So it's 1-chloropropane and it's sodium hydroxide. So we're just going to swap the halogen for the hydroxide and you end up with NaCl as a byproduct. But again, you could do the mechanism for that because we're going to go into that now, do the mechanisms for questions 2b and 2c and then write the equation from that. So I will get rid of this top half. In fact, I'll get rid of 2a as well and I'll keep 2b and c there so we can see it. And I'll set up my board. So I'll do 2b here and 2c. So 2b, so I've got CH3, there's the iodine. Okay, and I've got my ammonia as my nucleophile. Have to show a lone pair. Please, please, please do not put a negative charge on the nitrogen because ammonia is a molecule, therefore the number of protons equals the number of electrons. There is no overall charge. If you want to put charges on the N's and H's, if you drew it out display formula, make sure it's delta negative and delta plus in the correct order. But again, I'm not going to put any partial charges on because I don't really need to. I'm going to show from the lone pair on the ammonia, attacking the carbon, and then the carbon-iodine bond breaking like so. And then you end up with this ammonium ion intermediate. And here you do need the charge, positive. And then you'll need the second molecule of ammonia. I'm going to draw this one out the other way around to show you the opposite way. That will take a hydrogen, the NH bond breaks back to the nitrogen, and it should give me CH3, CH, NH2, correct? CH2, CH3. So again, it might be easy to do the mechanism first for that one and then write the equation. And the last one is simply nucleophilic substitution with hydroxide. So we've got 1 chloropropane. Okay, and OH minus is our nucleophile. Charge on this one, so the ammonia, there was no charge. Hydroxide is an ion, so there is an extra electron and there is a proton within it, so we have to include it. And then back. And you end up with the product. I'm going to draw the product out because I already know what it's going to be. You're going to end up with propan-1-ol. So that takes care of the halogenoalkanes B, all right, activity. Let's move on to halogenoalkanes C, the final one from today's work. Okay folks, the last part of today's task, got the names of my worksheets mixed up. It's halogenoalkanes B we're going to be looking at now. The final one, which has got all the mechanisms for nuc sub and elimination. So this one, it tells us that we've got, just read the top of that to you, we've got 2 bromo, 3 methyl butane, which is that, and we've got hot ethanol potassium hydroxide. We get a mixture of alkenes and an alcohol. So the alcohol is formed via nucleophilic substitution. Okay. So again, I'm just going to demonstrate that. Here's my hydroxide ion, here's my halogenoalkane. So I'll end up with this product. I'll use skeletal form to save space. So you end up with that, and because you're using potassium hydroxide, you'll end up with KBr as a product. And I'll let you figure out the equation from that. The potassium ion is obviously a spectator ion in this whole process, so it's just that plus potassium hydroxide makes this plus this. Naming this, so would be 3 methyl butan-2-ol. And what is the role of hydroxide in this mechanism? Well, it's nucleophilic substitution. So the hydroxide ion is acting as the nucleophile. Okay, so it's acting as the nucleophile, the electron pair donor, and it's attacking the delta positive carbon. I haven't shown it yet, but I'll show it now. That's polar, because the bromine is more electronegative, and the carbon-bromine bond breaks to produce the bromide ion, which ends up as potassium bromide. The alkenes you get, well, let's just clear the mechanism and then talk about the alkene half of the board. So I'm just going to get rid of my blue curly arrows. So hot ethanolic hydroxide producing alkenes, the mechanism is elimination. Sometimes you'll see that called base elimination because the role of the hydroxide ion now is in fact a base. By having it in hot ethanol, you're going to more likely go down this pathway, but some of the hydroxide will still act as a nucleophile. Right? To encourage more nucleophilic substitution, you change the conditions from hot ethanol to warm aqueous. So during elimination, right, what happens is the hydroxide acts as a base, which is a proton acceptor. It is going to accept a hydrogen from a carbon, which is adjacent to the carbon-halogen bond. So it's either going to take that one, or it could take that one. All right. Now, if it took the orange hydrogen, the double bond would form there. If it took the red hydrogen, the double bond would form there. So I'll try and draw both products out. So you end up with that thing there. If it was the red hydrogen, and if it was the orange hydrogen, you'd end up with, so it's going to be that. All right, so naming these things, this would be called 2-methyl-butene, and this one would be 3-methyl-butanene. Okay. You don't need the 2 for this particular one here, but you will need the 3 for that particular one there. I'll show one of the mechanisms then. So we'll attack the orange one to show you how that's going to look. So 3 curly arrows, bingo, bango, bongo. And then in each case, whether you go to make the orange product or the red product, the byproducts are still the same. So the OH minus is going to take an H to make H2O. Yeah. And the bromide ion, the bromine atom has fell off as a bromide ion and will form the potassium bromide. So you're going to get that and that produced, whichever of the 2 hydrogens you take. And like I say, always check your products as well, because they're quite sneaky with this. Is there any EZ isomerism in your products? Well, if we check here, no, you can't differentiate between these 2 methyl groups, so there's no EZ isomerism there. And there, well, the double bond's at the end of the chain, it's got 2 hydrogens on it, so you can't differentiate there. So potentially you could end up with 4 alkene products if it exhibited EZ isomerism, but this one, it doesn't. So again, base elimination or just elimination. Hot ethanol, you get a lot of base elimination happening with your hydroxide ions. With warm aqueous, you tend to end up with more of this, although you still will end up with a little bit with it dissolved in hot ethanol. And that concludes this week's work. Okay, enjoy.